Hi, everyone, and welcome to the MLOps podcast. I am Dean, your host. It's just a pleasure to have you here. And today I have with me Assaf Pinhasi. Assaf is an expert, hands-on MLOps and ML engineering consultant. He helps companies deliver real-world machine learning products by building well-engineered systems. He was previously VP of R&D at Zebra Medical Vision, a company building deep learning medical computer vision solutions. He was also the director of PayPal's Risk big data platform, building data pipelines and infrastructure at very, very large scales. He's done a bunch of additional awesome things in the world of data and machine learning, and he has a lot of interesting thoughts, which he also shares on his LinkedIn about how to get machine learning models into production. So I think it's pretty clear why he's here, and I'm happy to be talking to you. Thank you for taking the time.
Thank you. Thanks for having me.
Awesome. So your career, I think, is a really strong mix of software engineering and data science. I'd love to hear you share a bit more about your path and maybe how it's framed your thinking about machine learning and machine learning engineering.
Sure. Yeah, that's a great topic, actually. So, kind of looking back at where it all started, I think I'd probably say that my first kind of exposure to analysis and analytics in general was probably during my military service. This is back in 1996. So at the time we were doing primarily kind of ad hoc analysis to try and work out the implications of raw collected intelligence data. But then kind of towards the end of my military service, we kind of stumbled upon this idea of trying to crunch all of the data that we've collected in old-fashioned mainframe systems and in siloed databases into something that has more kind of large-scale meaning, doing all sorts of kind of classic BI and also some graph analysis. So this is kind of the first exposure that I had to this topic. Then I went to study computer science and math in the university, and I kind of realized that academia wasn't for me. I was very eager to get my hands on, I completed my studies, but I realized that I'm not going to continue to do advanced degrees. And then kind of in parallel to studying university, I started working as a kind of a data scientist. They didn't really call it that at the time. This is probably 2004 for an email security company. And, kind of using SQL and scripting to kind of detect all sorts of malicious email activity, be it spam or security viruses and stuff like that. So I kind of trained some models then, wrote a lot of scripts. And it was interesting because I came from the military background, and from the sort of work that I was doing was really very analytics focused and data science focused. And our peers at the R&D were always commenting on how the team of folks that were doing this analysis were always crashing the databases and always stretching the infrastructure or trying to get them to implement stuff in production that made no sense to their paradigms, etc. So I was on that kind of side of challenging the production system and stretching it to its limits. And after completing my studies and this role, I joined a classical software company, and this is really where I got my kind of classical engineering training, doing mainly backend and database layer engineering. I realized that I really love engineering. I had terrific opportunity as the first job as a graduate to really learn from very, very experienced people, and also building platforms for other engineers in the company. So it was super fascinating. And then, like you said, I joined PayPal. I joined when the team there was very small, and really I joined to lead the data engineering team. And kind of looking at the back and forth, right? So again, now I joined another company, and now I was working with data scientists, working with analysts as an engineer. And initially it was very ironic. Initially I really had no patience for the lack of methodology and discipline, and then their lack of of coding standards. I completely turned to the other side, and now I was the engineer commenting on other people's level of code. But sort of over time, I kind of realized that the products that we were building there, like very complex analytic applications that crunch all of PayPal data in batch and then in stream, that then become features in models and stuff like that. I kind of realized that, I was really I really felt the fact that I was uniquely positioned to work alongside these data scientists and together come up with an actual product that would make sense, right? Making these really tough trade-offs between what they're trying to achieve analytically and what the system can actually support, how to turn this into something that's actually a well-engineered system. So that was a real revelation. It took me a while to realize that it's this combination that makes it the most interesting for me. And then the second thing, of course, at PayPal was, even back in 2010, PayPal was really like the risk organization with PayPal was really like kind of a powerhouse for machine learning. There wasn't that much open source projects or even that much written about machine learning in production, but PayPal was doing it at a very large scale already back in 2010. Not that many companies probably in the industry, maybe apart from the really big ones, were doing that. And everything we were doing there was really stretching all the infrastructure to its limits. So I kind of learned a lot about, these kind of production level trade-offs of, how to optimize models that need to inference on many megabytes of data per hundreds and thousands of requests per second. It's actually a very fascinating career there.
Interesting.
Yeah. So it's this kind of back and forth.
No, I was contemplating if I should wait to hear everything or interject. I'll ask one question, and then the last part, or at least what I know as the last part, is the last two parts, I guess, are also, I think, really interesting. But here already, it seems like you literally did like one job as a software engineer, one job as a data scientist, intermittent until you settled into the sort of ML engineering side and things like that. I'm curious. Like to dive into PayPal for a moment. So you're saying like really large scales, really early on, not a lot of written content. How do you make your way about? I feel like there wasn't a lot of written content about machine learning in production. There wasn't maybe a lot of content written about machine learning at all. So I'm curious, like, how do you build all of this infrastructure and tooling around something where you have no reference point? Like today, I've interviewed a lot of people and they have at least some reference point from like the large organizations. But if I understand correctly, you had none such things. So how did that work?
Sure. It was a very long and challenging process. That's how it worked. And I think overall, the risk organization with PayPal is quite a large organization. It was, a couple of hundred people, even when I joined, I think. So clearly there are different kind of skill sets within that organization, right? There were people who were at the time focused on building the models that do the risk evaluation, right? And there were like quite a serious team of mainly PhDs, very little engineering skills to speak of there, and of course we had folks like me who were like in the infrastructure domain, but also working alongside the data scientists to kind of build their pipelines and build their infrastructure, and of course PayPal grew kind of over time in terms of the number of models, the complexity of the models. So back in 2010, it was a lot of regression, like classical regression models, and neural networks started coming up, maybe in 2013, 14, which of course created a new challenge in terms of compute and in terms of hunger for features to feed into the model. So it was a continuous effort to kind of try and balance these functional requirements, non-functional requirements, the growth of the models, the growth of the features space that we were using, very large feature space. So it's continuous trial and error, really.
Fair enough. I guess, yeah, when you don't have a reference point, then trial and error is probably the best and only way forward. I guess, in a sense, what you're describing is building out the internal ML platform from scratch, which is something that people still do every now and then. But you did this sort of like on hard mode. I'm curious if the approach was like, we're going to tackle use cases like model training, then model deployment, then monitoring, then I don't know what? Or was it more like we're going to solve an end-to-end flow for one team, then try to generalize to other teams? Like, how did that work?
Yeah, so at the point where I joined PayPal, there were already models in production. That's important to
Mm.
say. They weren't being trained very frequently. The features that
Mm-hmm.
they were using were relatively simple.
Okay.
But what we had, and at the point that I joined, there was already a very live and working system that was already functioning. And then we mainly had to kind of evolve the scale of everything over time. And the scale
Mm-hmm.
did break quite a few of the paradigms. So, for example, on the pure modeling side, the predictive power, for example, of classic regression models simply broke, simply could not reach the target performance that we wanted to get. So there had to be kind of a step function in terms of the modeling capability, right? In
Mm-hmm.
2010, where I kind of joined, the main thing that I introduced was kind of what we call today big data, right? So I kind of
Mm-hmm.
introduced Hadoop back then to
No.
calculate very, very large scale features in batch and serve them. And as
Mm-hmm.
I started doing that, we kind of realized that we had this kind of offline calculation platform like the offline store, but the online store just couldn't handle the amount of data that we were trying to store there for serving. Right? We didn't call it offline online store; it was just like the database. Right? But so the ETL had to be rethought, and the whole kind of how we access features in production had to be rethought. Um, and then model monitoring started evolving. Like we realized we were having too many production incidents around model performance dips. There were PayPal. It's a very significant impact when a
Mm-hmm.
model is underperforming.
Yeah, I can
Um,
imagine.
yeah, so it was like trying to figure out, okay, how do we log all the predictions from production? How do we create jobs that monitor and create dashboards and have team? So it was kind of like each time we tried to scale something, something else broke, and we had to kind of figure out how to what's the right engineering solution and what's the right trade-off in order to be able to meet that next level of scale. So that was really the path.
And one last question about this. So you are very familiar, I imagine, with all of the tools and platforms that exist today. Probably some internal platforms and some off-the-shelf ones. How would you compare like building a platform at that time to the solutions that there are today? What's easier? What's harder? I don't know, things like that.
Sure. First and foremost, the data platforms themselves, right?
Mm-hmm.
The sort of technologies that exist today, even irrespective of specifically machine learning, just the
Yeah.
level of maturity of, say, Spark, the different vendors that you can get, or key value stores, or managed key value stores, servers, Kubernetes, all these sort of things. Just the infrastructure level has matured significantly in the last 10 to 12 years. So already that's a much better starting point than
Mm-hmm.
needing to kind of manage your own servers. We were running inside a data center. There was no cloud, there was no auto scaling, there was physical hardware.
Yeah.
So that's one aspect. I think I don't really know what's happening there today in terms of the infrastructure. I think that, of course, for simpler use cases, for use cases that run in lower scale, I think the starting point today is there's no comparison, right? So you have so many tools and platforms that you can kind of put together and start running with versus needing to build them from scratch. I do think that at the scale that, for example, PayPal was even just like a few years back, it's not trivial to move to these kind of off-the-shelf products, right? Because
Mm-hmm.
there's a lot of there's a lot of optimization that's gone down into every single aspect of the platform that is not easily replicatable or replaceable by a third-party tool. But I think this is the case with many kind of in-house platforms. Once you build them, they're typically there to stay.
Yeah, fair enough. Okay, so continuing sort of your path, so you finished your role at PayPal, and where did you go next?
So then I kind of joined a young startup called Zebra Medical Vision that was set out to build a kind of autonomous radiologist. So being able to ingest X-rays, CT scans, and other kind of medical imaging, and be able to diagnose them to the same degree that a radiologist would. And kind of joined at a very interesting point. It was 2017. Deep learning was still pretty nascent domain. So, of course, it started, things were happening in this domain, but it certainly wasn't as mature as it is today. And and also at a very interesting point in terms of the company's level of maturity, right? So the company was kind of trying to figure out, what does it mean to build a deep learning based product for this domain? And at the time, I started leading the R&D that included leading the research team, and had to do a lot of catching up around computer vision, because I had no idea what computer vision was when I first joined. But really, here was an interesting learning in terms of this exposure to a product that's based on deep learning that has very, very rigid performance goals, right? So in terms of model accuracy, sensitivity, specificity, etc. So the bar for what it means to build a product in this domain using computer vision was very, very high. And going through this process with the team, with the management, with the product, of what does it mean to actually build a product that is with that level of accuracy in a domain that's so complex, the medical domain. This was probably one of the most fascinating learnings that I got from Zebra. The result is that I kind of today, when I hear about models, the first thing I start thinking about is, how do you know that your model is working correctly? How do you test your model? How do you evaluate its performance? How do you even define what a useful model is? That's my first thought when anyone tells me about a new machine learning model, because it's very easy to gloss over performance issues with aggregate statistics.
Yeah, and I guess here as well, you went for hard mode, because the main difference between a product like Zebra's and maybe a different computer vision based product is that there are objective standards you need to meet in order for this product to be used, because it's medical. So there's the FDA approval process and everything, which I guess I don't think a lot of people know this, but I think we started Dags Hub towards the end of 2019. One of the first companies we went to speak with was Zebra. We spoke with the CTO, with Eyal, and I remember him explaining what you guys are doing, and thinking wow, I think this is the first real hardcore computer vision product that we've spoken to, and it seemed like definitely at the time you were leading the pack with respect to actually having these models do stuff in the real world. And I remember discussing some of the challenges with getting these models to clear the bar that the FDA sets for something, so that hospitals and doctors would actually get value out of it, and thinking there are a lot of very unique challenges that, as you say, maybe you can gloss over in other places. It does a decent enough job, so we get something, we can push it to production. We have whatever proof of concept MVP style thing, but here that doesn't hold. You have a baseline, you have to clear that baseline, otherwise you have a problem. So I'm curious, and also I guess for you, was this your first time working on non-tabular data science, or?
Yes.
Okay.
definitely.
So those 2 points are interesting to me. Like, first, what did it feel like to transition from like a career in working with tabular data, even though like very large scales and a lot of unique challenges, and then working on unstructured data, and then also for like how does it work when you deploy a model and you can't fool yourself? You actually have to do really well, otherwise it's not going to be used.
Yeah. So I think the transition I'll start with the first one, with transition to unstructured data. So I think one of the things that people who work on tabular data um, kind of take for granted to a degree is the ability to do exploratory data analysis, right? So I'll just do a bunch of, I'll just profile my data. I just, I'll just see, the distribution of each feature, and or aggregate or look for outlier values and clean the data, so I can interact with my data from a notebook and just visualize the aggregate result of this data. And the first thing that you notice when you transition to work with unstructured data, and especially images, and in this case, a radiology scan, for example, a CT can contain 250 to 500 slices, each of them, have half a megabyte of data. So, and you have many tens of thousands of these CTs to analyze. Is that every tiny thing that you're trying to kind of reason about requires you to think differently about how to access your data. What do you ask of it? How do you summarize the information that's in it? And how do you kind of develop an intuition for this data, right? This is even separate from the medical domain, which like you can see a medical image and have no clue what you're seeing, right?
Yeah.
So even the domain understanding is a tricky here, but from a technical perspective, and I kind of found that that the data lifecycle for deep learning application was and still is, I think, to a great extent, a very underdeveloped area of focus. There are still very, very few tools and standards that actually make it easier to manipulate this unstructured data at scale, and to figure out what do you have in this data, and how do you kind of build stratified data sets out of it, or find edge cases and stuff like that. I think this is a very nascent field still. So that was definitely a huge challenge. And then, and combine that with, it kind of ties back into the need to have, to set yourself at quite a high bar in terms of performance. So I think, the FDA is, like you said, it's, it requires for you to demonstrate efficacy and safety, and to do this in a very kind of scientific way. So you need to be able to prove your model's performance under multiple circumstances, in the presence of multiple artifacts and images, and in conjunction to human readers. And there's a lot of know-how about how to approach this, but kind of tying it back to the whole unstructured thing. When you need to build data sets that represent a very broad array of long tail cases, in order to demonstrate that your model does not screw up over these long tails, this is when things get really, really complex, because you're sitting on, say, you're sitting like Zebra, or sitting on very large piles of medical images, but fishing out these edge cases was a huge effort, and building the data sets for evaluation and for testing was probably the biggest effort in every project, much more than the modeling itself, because it required you to really gain mastery over the domain, the specific medical question you're trying to answer, and then project it onto your data and find representatives for every possible medical situation, comorbidities, etc., etc. So this was definitely the combination of these two made the data really the biggest bottleneck, or the data in its structured form, the biggest bottleneck.
This is interesting. I feel like the way you describe it, this really connects in my mind to the presentation that Tesla did in their AI Day about hard example mining for autonomous vehicles. In both cases, like human lives are on the line, and the amount of data is huge, but the amount of useful data might be much smaller than that. And so separating the useful stuff from the non-useful stuff is a really, really hard task. I think in their presentation, they did give some hints on how they do it, and including a large sort of a large effort around data simulation and things like that. I know that that's harder to do in the medical domain. So as much as you can share, I don't know, maybe this is like a proprietary information, but how did you handle that in your case?
Yeah. So I think I can't really divulge that many. I'll just juxtapose it a little bit with what Tesla is doing and can do. Right? Tesla has the ability to run inference at a very large scale and collect a kind of weak supervision from drivers. Right. So if the model thinks something, but the driver behaves maybe later on in a way that might indicate that there was a mistake, right? So the driver overrides the model's decision, or the driver makes a decision that's contrary to what the model said. You can use that as a kind of an indicator to go back to your data and figure out what just happened there, and maybe you can fish edge cases out of that. In radiology, it's a little bit, there is somewhat of an equivalent, which is trying to figure out what the radiologist thought by kind of reading, using machine learning, of course, reading their reports and being able to kind of maybe gain some information from what the report said, what the radiologist wrote. But this is a very noisy signal. That's one thing. And the second thing is you need to be able to kind of narrow your data iteratively. So I called it kind of positive fishing or mining. Right? So so for example, you would develop, it's kind of like an active learning just to find examples. So you train a model on a certain data set, you run it in inference on a much larger data set, you take the high confidence examples and you start sifting through them and kind of categorizing them. But then I think there are other techniques that tend to be kind of domain specific. But I think one of the things that I'm still discovering how underutilized the technique is to just do a very thorough error analysis on large data sets. It's painstaking, but this is the best way to figure out things that you weren't prepared for. So I think we invested quite a lot in doing that, and through that we really gained a lot of understanding into our models' performances, and we're able to then improve them using this technique.
That makes sense. Yeah, I know that there's a bit of tooling being developed around sort of data error analysis and data debugging, model debugging, however you want to call it. Seems like it's still a nascent field, so that makes sense that you'd have to invest sort of some of your own engineering time in order to do that well. So I guess moving on to today, how do you describe what you do in your day-to-day today?
Right. So basically what I do is I work with companies that are exclusively on the domains of data and machine learning. And really what I do is anything, like I tend to be like a full stack architect. So I start from exploring the challenges. Typically companies that I work with have already done like one iteration of deploying stuff, building stuff, running stuff. They have models that are running in production. Typically want to take it to the next level, and have come across barriers or roadblocks. And typically what I do is I would start from the architecture side, specify the system, educate on best practices, formalize the requirements, do the system design, do the technology selection, etc. And then more often than not, I find that, especially over the last 2 years, I usually take on part of the implementation hands-on, and kind of help the team get started by building the first version of whatever is the most critical piece of infrastructure that's needed.
Interesting.
Yeah.
And what's the division between structured and unstructured data today in your work?
I would say about 50-50.
Nice. That's
Yeah.
good. That means it keeps things varied.
Yeah, that's right. And also I work with all sorts of companies, right? So from very small startups like that don't have any engineering to to corporates, global corporates that have hundreds of thousands of engineers.
Fair enough. So you could say it's safe to say that you have a lot of experience with machine learning in production. And so I'm curious, this might be a trivial question for you, but I think it might be interesting to our audience. So what in your experience, what does it mean to do machine learning in production, and what does it mean to do it at scale?
Right. So I think before the interview, I kind of I asked a large language model that shall remain nameless. What does the model think putting machine learning in production means? And the response I got was, I'll read it to you because I saved it. It was quite elegant. The model said that putting a machine learning model in production, it means to make it available to users and to ensure that it continues to work effectively over time.
That's good.
Yeah, pretty good. So I think if you kind of take this apart and unpack this, there are kind of three components to the answer. One is to make the model responses available to users. Implicitly, what it means is have the model impact business decisions, and typically in an automatic manner. Have it be effective, like have the results of the model be effective, be good, have high level of efficacy, and keeping it running well over time. So these are the main components, and I guess applying them in practice tends to be a problem that could often is a little bit domain specific or context specific. So for example, let's first look at the stuff that's the family of use cases that are starting to take form and be a bit less context specific. So when there are certain conditions in which when the requirements are not especially challenging, and we can go through what dimensions of requirements can be challenging. The act of putting models in production is starting to take some sort of a form factor, right? So it's starting to become a better understood practice that you can really kind of create direct analogies between what people are writing about on the internet and what you should be doing. This is when your problem scope or the challenges are what I think a smarter person than me coined the term reasonable scale, right? So reasonable scale in the context of I think it was here on this blog, on this interviewed with you. So yeah. I think it is starting to take shape what it means to do this kind of deployment of models in production when the scale is, or when the challenges are a bit more modest. And I think when you kind of look at the form factor, I think it's becoming more clear what it means to specifically what are the steps and design considerations that you should take when, for example, when you're building a recommender system at reasonable scale, when you're building a fraud model at reasonable scale, when you're building, marketing or lifetime prediction models at a reasonable scale. This kind of department is starting to take shape as more of a starting to gain a form factor there. But I guess the challenge is to know whether, oftentimes the challenge is to know whether your use case fits that mold, right? So um, because it's very easy to take almost any one of the, and there are multiple dimensions to each machine learning problem, tweak it a little bit, and then all of a sudden it's much harder to follow a well-known form factor. You need to find a solution. Finding the solution is often a system level optimization process. You touch one thing, let's say, for example, let's give the example from risk model, make it more concrete. So risk models running at a reasonable scale. Let's say that you have a few tens or hundreds of requests per second. Your models are running XGBoost, and you need to, you maybe have like 30, 40, 50 features. Most of them are aggregative and built in batch. This is from the inference side. Of course, there are other dimensions, but from the inference side, this is a reasonable scale problem. And the problem, and what happens when you need to scale this to hundreds of features, each of them containing, they're not scalars anymore, they're embeddings. You have tens of models that need to run for every transaction. You have thousands of transactions per second. And you have low latency. And now you need to kind of play with all of these components and figure out how do I take a huge bandwidth of data and funnel it all the way to a model that can make a decision in 50 milliseconds. This is a system level exercise. It's not just an engineering exercise. You need to make a lot of trade-off between how you represent the data and what kind of predictive capabilities you need. So
no, I think
sense?
that makes total sense. I think that the way I sometimes think about scale is when you can no longer have your cake and eat it too, and you need to start making trade-offs because you have to be able to consciously articulate what you want to prioritize and be willing to trade off other things to get what you want. And specifically, the point you made, I think was interesting. I was sure you're going to make this other point where people have a tendency to overcomplicate. So you have something that, like, you can do a minor tweak and have it fit into the reasonable scale stuff, but you insist on, I don't know, having a more complex feature or something like that. So you have to rebuild everything from scratch. But the point you make, I guess, works both ways in the sense that you might now be in reasonable scale, and then like two forks in the road, you suddenly arrive where you have to customize a meaningful part of your platform or tooling. I'm curious, like if I'm representing the audience, which are mostly practitioners thinking about what to do in different production sort of use cases, the question that then comes up is like, what is the common denominator? Like, what's safe? And I can just, use something that's usually generalizable. In most cases, I'm not going to end up breaking it the day after tomorrow. And what's usually the more customizable parts of the platform that I need to be sort of conscious of?
Yeah. I would say that there are parts, if you're talking from a stack perspective or from a platform perspective, I think the kind of parts that tend to be a little bit more stable and are less use case specific are typically data sinks. So anything that data goes into and doesn't need to come out of that much or doesn't integrate that much with downstream stuff. So, for example, experiment tracking systems have kind of emerged. There are a bunch of vendors. I know a few, but this kind of piece of infrastructure where most of your information lands, and typically for most experiment tracking systems, this is where it stays, or you eyeball it and report on it. But I think this is a good example for where you can start and pretty much trust that it should serve you going forward. Same for model monitoring. I mean, there are nuances there, and of course, monitoring structured data, monitoring unstructured data, support for features, but overall the form factor there is more agnostic to what you're monitoring than other types of infrastructure. And I think also to some extent inference as a whole, as a paradigm, it's starting to it's starting to be a bit less chaotic than it was a few years ago. So you're starting to see more design patterns, more things that you can kind of reason about. Okay, you need to ask yourself about throughput, latency. If you have tabular data, where are you going to get the features from, right? And if you need a feature store or not. People understand that they need to do logging, so log the predictions and the feature vectors if they're doing tabular, and also the raw data if they're doing unstructured data, in order to continue to build the data repositories. The concept of shadow and A/B tests, you can ask yourself, do I need it? Do I not need it now? And kind of be able to have this as be a checkbox in your infrastructure platform. I think these are the areas that tend to be somewhat easier to reason about, or at least make a choice that you're probably going to walk into this choice with your eyes wider, open more widely. Put it this way. And the stuff that I mean, this is just to contrast it, right? So this is in stark contrast, in my opinion, to data. How you run your data operation around even a reasonable scale model that has enough business value. This tends to be a very, very domain specific, very, very company specific. It's highly impacted by previous technology choices in the company. Which cloud vendor are you on, and where's your data lake if you have any, and where's your data warehouse if you have any. Your quality measures, your exposure to risk around data. These areas tend to be, in my experience, more domain specific or problem specific, and need quite a lot of reasoning before you get them right.
Interesting. So I really like this. I don't think I've heard this sort of mental model before, where you're saying the things that tend to stay the same are the things that are just like destinations as opposed to sources. And that sort of makes sense, because if it's an endpoint, then you don't care as much. It just needs to get there. And as long as you get the stuff you need to be there to the right place, it'll be fine. I guess one interesting exception, at least from my experience, I'm curious what you think about, to this rule might be orchestration, like managing infrastructure for training at large scale. So arguably you could say it's not a source for anything because you just send the data there. But at least from my experience, it's still very, very custom. So I'm curious like how you think about that and what these solutions are.
Yeah, I mean, just kind of to defend the paradigm of sources and sinks, I think orchestration is by definition a source, right? So because it's right there in the middle of all your pipeline and all your activities, and not just like a place where data gets dumped.
Fair enough.
I think I find that this is probably one of the areas that people get the most confused about, the orchestration platform, or
yes,
because it touches on deep exposed nerves of DevOps, and the cultural chasm between DevOps and research, and people have religions around this particular area.
Yeah,
I find that teams who are doing reasonable scale development, that have a smallish team, they really should be focusing more than anything on their own personal productivity. That's the metric that they should be thinking about. The researcher's productivity, the researcher's ability to execute enough experiments without getting blocked by unnecessary complexities. And I think that from an engineering perspective, I always suggest that the core logic of whatever you're orchestrating needs to be very, very separate from the platform on which it's running. So I don't consider choosing an orchestration platform to be a one-way street. Like you can't go back on yourself on that. If you design your code correctly and you don't get too attached to particular features in the orchestration tool, I think it's very possible to transition with medium effort later on if you discover that you've done a wrong decision.
Mm-hmm.
But yeah, I mean, hearing and seeing the fear in the eyes of data scientists when they start hearing the word Kubernetes or Docker containers is always is always a good sign that maybe you guys should go on a different path here. Choose something that you feel more comfortable with.
Fair enough. I like that. I tend to agree. I think that the more common problem is analysis paralysis, where you don't choose anything because you're not sure if the solution is perfect. It seems to me like what you're saying, again, it tracks with what we're seeing as well, where these decisions, it's a two-way decision. You can go back later on. You obviously don't want to do this every other week because it's not going to be fun. But if it's like a next order of magnitude in scale issue, then your future self will be able to solve it as long as you're not doing something that has too much vendor lock-in. Like in the end, even if you hate it, under the hood, it's all going to be using Docker containers and Kubernetes. So as long as you have some infrastructure abstraction, you should be fine. I want to also spend some time on methodologies. So I think that like I've known you and been following you for a long while. I really like the way you think about the methodological and workflow aspect of sort of machine learning teams in production. And I think this is to all our detriment. Like there's a lot of talk in the data science and machine learning world about tooling and about really cool models and stuff like that, but not enough about how you should work at the personal and team level. So if you had to give an answer, I know this is a hard question, but what would you say are the core tenets of how to build a team to support machine learning in production?
I think like if we're taking the example we talked about before, right? So reasonable scale versus what happens when you have more challenges. I think overall the activities that machine learning teams need to be involved in tend to be kind of at a very abstract level. They tend to be similar, but their application tends to be very, very specific to the domain, the problem, the data, the constraints, etc. So I think overall adopting a kind of an iterative mindset as a team versus just as an individual, and be able to go through the loop of figuring out what your model should be doing better, figuring this out as quickly as you possibly can, investing as a team. This is the abstract workflow, right? And then you need to apply it to your domain. Investing as a team in building data assets that contain valuable signals over time. So making sure that your data continues to get better over time, continues to get not just from a data quality or data bugs perspective, but from data richness perspective, the amount of signal that you can derive from it. And then, yeah, I mean, these are the kind of tenets that I see, like be able to understand quickly where your model is not doing well enough, be able to constantly grow your data to have more signal in it, okay? And of course, to close the loop on this, you need to deploy hypothesis or models or test hypothesis models fast enough to be able to gain the understanding of where your model should be performing better versus get stuck in the lab between data collection and deployment. You spend a year and then you have no idea where you should be getting better all the time. No, I mean, it's just that applying this principle, even even for reasonably good machine learning teams, is still a challenge, right? Because a lot of things need to happen. First of all, you need to really understand your data and domain. You need to understand what would make your data better, and as a result, what can make your model better. I'm a great proponent of the fact that better data is typically worth much more than tweaks in hyperparameters. So better is in not necessarily scale, but better in terms of quality and signal. So you need to really understand the domain. You really need to understand your data. And then you need to go through the modeling cycle and the testing the hypothesis quickly enough in order to then look at the feedback and see where you should be getting better. And this, first of all, releasing frequently enough. Second, knowing what to measure when you get the results back, and not just like sit back and say, well, there's a 0.3% difference in accuracy. Which one is better? Much more, ask the question in a way that's much more relevant to your domain, not just in an aggregated fashion. And kind of be able to understand what's the next tweak that I need to do. And going through this cycle tends to be quite difficult, both from a technical perspective and from a mindset perspective, in my experience.
Yeah, I think that the iterate fast part is especially like, first, I think the overall theme of what you're saying is basically, in a sense, we a lot of people call themselves data scientists, so they have the word scientist, or ML researchers, so they have the word researcher. But I think that formulating hypotheses and then going out and testing them quickly and getting responses, like, this is the essence of what those words mean. And a lot of times we want to dive into the nitty gritty details of the architecture of the model and everything. But in the end, if you're not testing, if you're not deploying this to production and actually seeing how your model is going to perform when actual users use it, as the unnamed large language model told us earlier, then you're missing out. Like, I think this also relates to one of the points that I probably made like 10 times on this podcast, but I really think it's important that people tend to do this sequentially as opposed to iteratively. So you're like, I'm setting up my data platform, so now I have to have the best data platform that supports all of the future maybe features that I might need, and then I'm going to do training and experimentation and deployment and everything. And what we usually recommend is like, get to production as fast as possible. It can be a if-else model, but at least you'll cover the entire flow, and then start iterating on what works worst. Like, maybe in the best case, I agree that it's not that common, but maybe in the best case, you get to the point where an if-else model is really good and it solves your problem. And then you solved a lot of unnecessary pain and challenges that you don't really need to deal with. So I think that really connects. And I think this is really golden for people that are trying to reason about how to build a team, because it's not just the tooling, it's not just the model architecture, it's not just the amount of data, it's sort of conditioning ourselves to think about the problems that come with this field in a way that we can solve them, even if the problems tomorrow are a bit different. So yeah, exactly. Thanks for sharing that. I think that's great. Yeah, go ahead.
And just to add on what you're saying, I agree completely. And I think that I guess this is not really a revolutionary statement, but the core reason why people or teams tend to work in this waterfall fashion is really a cultural thing. It's a cultural issue, and the cultural issue is sitting on the multidisciplinary chasm between data science and engineers, in my opinion. So the attempt of each one of these disciplines to silo themselves, build their own part, and hand it over tends to be something that will result in what you're describing, meaning first I'll build the best data platform, but as soon as I finish it, the data science team will say, what the hell did you build? It's not useful for me because I'm going to build the features like this. And then the data scientists spend a long time getting intimate with their model before you hit production. So I think the core reason why this happens is the multidisciplinary gap between these two disciplines, and the fact that none of out of the I'll get to it maybe later, but up until maybe a year or two ago, uh, people who worked in engineering, there were very few people who could really empathize with the life cycle of a machine learning model. And data scientists who came out of academia could really not begin to understand what a machine learning system should look like in production. And of course, this chasm is what caused slow and error-prone and risky machine learning models to fail. In my opinion, the solution is always the synergy between these disciplines.
Interesting. So this is a good segue into my next question, which is who should be responsible for production? Like who is it the data scientist or the software developers, DevOps, whatever that are responsible for this ML work when it's deployed?
I think that the scope of role definitions in this in the machine learning space is very very fluid, and I think that sticking to titles or getting too obsessed about titles is maybe a little bit counterproductive at this point. I think I tend to look at machine learning efforts as a team effort, and in this team you need different skills. You need people who understand the business domain well enough. You need people who really understand the data. It might be the same person, but you need people who really understand the data, who specialize in the data that's specific to the domain. You need people who know how to model, and you need people who know how to engineer systems. And then on top of them, the orchestration level of the team needs to be a dialogue around system level optimization. So being able to see, it's not enough that you have all these disciplines in the team, they need to be able to talk amongst themselves. So there needs to be some centralized orchestrator that's able to talk and consolidate all their perspectives into a holistic system that would actually work, that would trade off the right business outcomes, the data limitations, the modeling challenges, the engineering challenges, and create something cohesive. And if you treat machine learning efforts that are aimed at production as a team effort in which you require to have all these skills, then it's less important if the title is data scientist or the title is MLE or the title is DevOps. The level of skills is that the individual people in the teams have is constantly evolving, right? So a few years ago, it was virtually impossible to find a serious data scientist or a deep learning researcher who had any idea about engineering. And now this is becoming slightly more common. So instead of sticking to the title, think about it as a team. The team needs to be able to do all these things. If the team is able to do these things, then the team owns the service. So it's fine. It's handled.
I like that.
That's my perspective, at least.
Yeah, that seems like a healthy perspective. There's a lot of, as you say, job title discussion, which is probably not super productive, even though a lot of people really enjoy it. And the skill set part is actually what's important. I want to go over three maybe shorter questions. We'll see. But they're a bit higher level. So first one is, what are your predictions about where machine learning and MLOps are headed?
There are many predictions, but maybe let's stick to the previous topic, which is about roles and skill sets and capabilities. So I think, like I said before, I mean, we're seeing a very clear trajectory towards people who have more of a diverse skill set around the combination of engineering skills and machine learning skills. It's coming from multiple directions. It's coming from researchers who learn through doing, like how to do enough engineering. It's coming from data engineers who are, working with data scientists, etc. It's coming from all sorts of transitionings are happening in this field, and I think that in the very near future, probably by the end of this year or beginning of 2024, I expect that your typical machine learning team will be comprised of mainly people who are a combination of the skills, machine learning engineers, I think they're called now, who are able to execute reasonably complex data science project in a production grade. And the number of kind of specialist researchers, PhD folks who came directly from academia, who are kind of remaining mainly on the theoretical side, will shrink. And I think that's one of the trends, and I think it's a good thing. So
I think a lot of
imagine
people listening would be really happy about if this prediction comes true. So yeah.
I think it's just the laws of physics are just pressing us in this direction. Yeah, and I think that still, I think it's going to be an amazing opportunity for the really talented researchers and data scientists who are very strong on the research side to guide, to be like the technical lead for the modeling side of the team, but have like 5 machine learning engineers who are just mainly focused on, executing and iterating on the research ideas and directions, even in complex use cases.
Yeah.
So that's one. That's in the machine learning scope. And I guess in the MLOps scope, I think I think we're due to some sort of a consolidation. I mean, there are probably about 4x more tools than anyone would ever need. And so in terms of tools and platforms, I expect there to be this VC winter is going to probably eradicate quite a lot of organizations that are not differentiated enough, not adding enough value. And I think that there might be an opportunity to consolidate a little bit more standard stacks that are more suitable for reasonable scale use cases. So I think that probably the companies that will succeed will be ones where they've managed to take a niche of reasonable scale machine learning and find very, very end-to-end, something that's enough end-to-end to make teams radically more productive than if they started to piece together their own tools. I think that's also kind of inevitable.
Interesting.
So these are my predictions.
Do you think that there's going to be success on the other end of the spectrum where you don't cover end-to-end, but you support extreme scale, like non-reasonable scale? Or do you think that there's not enough companies doing that type of machine learning that it's relevant?
From an end-to-end perspective, or from like a specific piece of the...
Yeah, like no, a specific piece. So like I'm sort of building this matrix, right? Like there's a specific piece and end-to-end, and then there is like reasonable scale and non-reasonable scale. So in that matrix, I understand you're saying basically like end-to-end at reasonable scale, like there are going to be some successful companies there. And then I guess we could cover each one, but the more interesting one, I guess, is like specific part and very large scale.
I think this is probably the most challenging area to build a company, because the form factor or the ability to create a useful abstraction that works across all use cases is very, very challenging. Again, the ones that tend to succeed are ones that are at least perceived as a sink. So, for example, companies that do labeling platforms, traditionally labeling was a sink, right? So or it's like a very clear interface. You just upload your images or your data, you get labels out, there's an API, it's very, very separate. So in principle, I think they've been around, or some of these for example labeling vendors have been around enough in order to evolve their offerings so that it can support very large use cases in some sort of a mature form factor. but I think other areas are changing too frequently to be able to nail down a solid product around them. In my opinion, that's kind of my experience.
That's interesting. I guess so I'm going to move to a totally different topic, which is you mentioned earlier an unnamed model, but assuming it was a different one, everyone is now talking about ChatGPT. I went on an interview a few weeks ago, and people asked me what's my take on it and the future of generative models. So I'm asking you the same questions, like where is this headed?
Yeah, I think like everyone, I was kind of astounded. It's really indistinguishable from magic, really, looking at this Chat GPT's capabilities, and kind of I don't know. I think the generative field of AI is kind of having its ImageNet moment, right? So it's like it's this kind of breakthrough where something that beforehand you couldn't possibly believe could happen now is proven, and there are benchmarks, and you can actually even touch it, which is, I guess, much better than ImageNet. Um, I'm guessing that this is definitely the beginning of a huge disruption in multiple domains. But I guess the way that I look at it is um, kind of going back to the experience that I had with um, building machine learning models for a medical domain. It's not the analogy is that to be useful for users, you need to take care of a lot of things. You need to build. No, it's not just the UX. It's you need to add capabilities that are domain specific, that are relevant to the use case, relevant to the workflow in which the user consumes the model, etc., etc. And unfortunately, I think it's still going to be very difficult to do that and really customize and tailor these large models to specific user expectations and contexts, because models are not directly engineered; they're kind of influenced. So, but um, I think that the large players out there are definitely, this is such a valuable problem that there's going to be a lot of research on how to customize generative models to in a way that doesn't require to reinvent the wheel there. And I think it very likely, unlike other models, for example, in classification and computer vision, you didn't really get a serious offering from a third-party vendor that just upload your data and get a great classifier. I mean, you have offers, but they're not serious.
Mm-hmm.
I think with the generative domain, I think the problem is so complex that it's impossible to solve in-house, this tuning or adding the ilities to these models. And I'm pretty convinced that the large players are going to go after this problem and create this as a service for you to kind of fine-tune and add the capabilities to larger models. But I guess we'll see.
Yeah, fair. I think that the one example that I can think of is like maybe it's a counterexample. I'm not sure, but the Jasper and GPT itself. Like if some people might not be familiar, but basically under the hood, it's using GPT-3, or at least it used. I don't know if at this point they trained their own GPT-3 from scratch, but the idea was basically to provide like copywriting based on GPT, and there are others. There's a Copy AI, which does something similar, if I'm not mistaken. And the like I tend to agree with everything that you said. Maybe except for the last part, which is I do think that there would be room for companies that are building applications to build on top of this and actually provide the use case. I do think that the larger people, like the larger companies that are actually training these models from scratch, have a very strong interest to provide those use cases as well, because that's the most like upstream value. Everyone wants to, like, that's where the big bucks are anyway. So I think with Jasper, like they're making significantly more revenue than OpenAI is publicizing. So yeah, so I think there's a lot of potential there, but we'll see. I agree with you. And I guess last question I have, which is again, like I think you provided a few of these along this interview, but tell me something true that few people agree with in machine learning and MLOps.
Something true that few people agree with. So are you hinting
Yeah,
that
like
what I
something
said is
spicy.
disagreeable? Something spicy.
No, it means yeah. Never mind. Go ahead.
Okay. So I think one thing that I found myself thinking about. I don't know if it's spicy enough for to match your criteria, but I've been thinking about when people talk about the need to retrain models as a terrible burden and kind of compare the speed in which your functionality decays between machine learning applications and classical kind of engineering, handcrafted engineering behaviors.
Mm-hmm.
So I think one thing that I've been thinking about is how, in a sense, framing this as a weakness or as a problem is actually looking at it the wrong way. Because if you look at the work that most engineering teams are engaged in doing, it's sitting in meetings with product managers, looking at results of their experimentation platforms and figuring out what's going to move the needle in the effectiveness of the application, whatever the user goal is, what's going to make the application more useful, and then planning how to execute on that, um, coding, arguing, building experiment flags and stuff like that. And I think if you kind of look at any kind of business as a continuous optimization loop,
Mm-hmm.
where the input is the software or the system that they're building, and the output is some sort of a user engagement metric that's supposed to continuously improve and grow. I think that maybe we're looking at the wrong way, and maybe in the near future, more and more companies will start to kind of automate these experience end to end, and turn this what's currently now a human guesstimation technique of what will move the needle to something more automatic, just at the core of every product. In which case, I think that definitely some of the tools around or the disciplines or practices around MLOps can probably become useful for such an optimization, right? So instead of having a system be optimized by engineers, just have the whole company be optimized in a continuous loop by software.
Yeah.
That's just a thought. I hope it was spicy enough.
It's. I mean, the maybe I'll add some implications to what you're saying that might make it a bit spicier. But basically, if what you're saying is sort of true, and this is the real direction that we're taking, that means that companies can achieve more with less, which means that starting a startup or a business might be much easier. But it also means that maybe a lot of companies are overstaffed compared to what they could be if such a tool exists. I think that there might also already be sort of early seeds of this. Like I've spoken to a company, I'm not sure whether or not I can share their names, I won't, but I've spoken to a company who's basically arguing that they can do this, like product analytics on steroids, where they make suggestions for how to improve your product based on your definition of what success looks like. I haven't tried out the product, so I don't know if it works or not. But at least in principle, people are actually trying to go after this, and I sort of really obviously I sympathize. Like building a company, you really want to understand what moves the needle most, and then you want to only execute on that. So if you had a solution that would tell you this is what's going to move the needle most, then you definitely want to try that out and see if it works and what the results are. But yeah, this is
I would say
interesting. Yeah.
so. Let me spice it up a little bit and just say that in the age of generative models that can generate code, it doesn't have to end with a recommendation. Right? So a lot of
Yeah.
tweaks can simply happen and result in code that automatically gets deployed as an experiment.
Yeah.
which is really
Then
close in the
the
loop.
AGI people start worrying, though.
I'm not sure that changing the font color or rearranging the page in CSS is going to be like a threat to humanity, but it might be a nice boost to businesses who are now limited in the number of experiments they can run.
Yeah, I think that it's definitely, as they say on 2-minute papers, it's definitely an exciting time to be alive. Being able to do all of these things with human readable text is amazing. Okay, so let's wrap this up. Recommendations for the audience, and it does not have to be data science related.
I think I will stick to the question around kind of machine learning skill set and how to kind of best prepare for this, what I predict to be a consolidation of skill sets. I think people who are now in the industry and starting to work in teams that are a little bit more heterogeneous, I think now is a great opportunity to systematically rotate within the team around the skill sets that you're applying. So say, in the next project, do only the engineering side, focus just on that, work alongside engineers, learn how to do it, do code reviews, learn Git. Don't try it all, don't touch data science. Learn the engineering hands-on in your next project. The next one, sit 50% of your time with DevOps and learn how to be a junior DevOps. Then do data engineering. Each project focus on one topic. And after maybe 1 or 2 iterations like this, that you go through the full stack, you probably know what you're best in, what you're most passionate about, but the amount of value that you can now add to a new project is much less bounded than before. And it can be just a couple of months in each domain, but focusing on one domain within the team. I think that's a great way to prepare for the future.
That's an amazing recommendation. I'm going to recommend one very generic, or not generic, but very non-data science related thing. So I'm very fond of recommending sci-fi books. I have now started reading the Architect. I think it's going to be a trilogy, but it's a series of sci-fi books by Adrian Tchaikovsky. I read the first book, which is called Shards of Earth. It's very, very good, and I recommend it. I'm now waiting for the second book, so we'll see if the second one continues being this good. But I think we can wrap up. Assaf, thank you so much for taking the time to speak with me today. It was a pleasure. I'm sure a lot of people will learn a lot from your experience. So thank you very much.
Thanks for having me.
And thank you everyone for joining. I'll see you next time. So bye.
Bye-bye.
Thank you for listening to the MLOps podcast. If you enjoyed this episode, please like the video or subscribe. If you have any feedback, leave a comment below. Thanks again for listening, and see you next time.